Motion retargeting is a central problem in character animation. While existing methods perform well when source and target share similar body structures, transferring motion across different morphologies, for example, from a human to a quadruped, remains extremely challenging. In these scenarios, preserving the style of the motion is particularly difficult, and results often appear unnatural or inconsistent with the target character. While previous motion retargeting methods have improved animation transfer, they rely on fixed skeletal structures and human-centered datasets. As a result, they struggle with morphologically diverse characters and often produce anthropomorphic motions instead of preserving species-specific movement. More recent cross-domain methods support different skeletal topologies but still rely on shared latent spaces, require retraining for each new species, and cannot perform true all-to-all motion retargeting. In this work, we present a cross-morphology style transfer method with semantic style alignment that enables bidirectional all-to-all retargeting with target style preservation, offering morphology-agnostic control without shared phase spaces or canonical skeletons, and scalable transfer without retraining. Our framework consists of two training stages. First, the motion generator learns a morphology-specific codebook of valid motions using a VQVAE. Then, with this generator frozen, an autoregressive code predictor learns to generate sequences of codebook entries from morphology-agnostic control signals. The motion generator receives the target skeleton together with sparse motion observations. The encoder compresses the motion into a discrete latent representation, where each latent vector is quantized to the nearest entry of a learned codebook, representing valid motion primitives. In the second stage, the motion generator is frozen. The autoregressive code predictor learns the temporal dynamics by predicting codebook indices from the control signals. A compact secondary codebook simplifies the prediction task while preserving a one-to-one correspondence with the primary codebook. At inference, control signals extracted from any source morphology drive the autoregressive predictor, which generates a sequence of discrete motion codes. These codes are decoded using the target skeleton to synthesize temporally coherent motion while preserving the target morphology's characteristic style. Our method transfers motion across different morphologies while preserving the semantic style of the target creature. In this example, human motion is transferred to a dog, yet the dog still behaves naturally as a dog. Motion transfer is fully bidirectional, guided by morphology-agnostic signals for semantic alignment. Here, the roles are reversed. The dog provides the source motion, which is mapped to a human animation. The transferred motion closely follows both the source trajectory and its underlying semantics. Without retraining, our method generalizes to new morphologies, enabling practical all-to-all motion transfer. In this example, a human running motion is transferred to a dog and an ostrich. Similarly, dog walking motion is transferred to a human and an ostrich. Finally, ostrich walking with a turn is mapped to both human and dog motions. Here, we show additional examples, including jumping and fast-running motions. We further demonstrate the scalability of our framework across a wide range of morphologies. A dog motion is transferred to characters with different body structures and control points, including a scorpion, monkey, human, ostrich, T-Rex, and dragon. Despite these anatomical differences, our method preserves the original action while naturally adapting it to each character's unique locomotion. Here, we transfer human push-up motion into the dog space, even though dog push-ups are not part of the training corpus. it can be seen that the dog's motion closely mimics the style of the human. A key element of our approach is that motion transfer is driven by control signals, capturing semantically consistent cues across species. Here, the same human motion is transferred to a dog at different speed factors, demonstrating precise cross-domain control over motion speed and style. Phase-consistent alignment is achieved through foot contact signals, ensuring synchronized turns, jumps, and transitions. In this example, an ostrich motion is transferred to human and dog outputs with accurate temporal alignment. Our method preserves the intended trajectory while adapting to the target's motion style. Even with differences in body size, gait length, or bipedal versus quadrupedal locomotion, the resulting paths remain spatially coherent and free of drift. We compare our approach to a skeletal-aware baseline, motion-to-motion, and the walk-the-dog methods. Our results exhibit superior motion quality and semantic fidelity, while the other methods struggle with retargeting or introduce artifacts such as foot sliding. The skeletal-aware baseline fails to support cross-morphology retargeting, producing unnatural motions and poor semantic preservation. Motion performance deteriorates when the database is semantically heterogeneous, often retrieving unsuitable matches. Walk the dog produces unnatural turning motions and does not consistently preserve the source semantics. In contrast, our method transfers motion across diverse morphologies while preserving both the action semantics and the target creature's natural style. We conducted an extensive ablation study to examine each component of our architecture. This example demonstrates the benefit of using a separate low-dimensional codebook in the gated recurrent unit, rather than reusing the original codebook from the autoencoder. Here, we evaluate the use of a gated recurrent unit, which more effectively captures long-term temporal dependencies than a multi-layer perceptron. Next, we analyze the impact of teacher forcing. Without teacher forcing, the model fails to converge due to compounding errors from its own faulty predictions during training. With full teacher forcing, the model suffers from exposure bias and generalizes poorly to unseen data. In contrast, using a mixed input strategy enables the model to both converge and generalize effectively. We also evaluate the contribution of different control signals used in our codebook. Finally, we compare continuous versus discrete latent representations. Continuous representations often produce overly smoothed motions that may lie outside the feasible motion manifold, whereas discrete representations generate more natural and physically plausible motions.